Hello, my name is Chris Bendel from Springer Nature, and welcome to the first of two panel discussions which we are going to be having today, and which is the culmination of 2 days of intense discussions from 25 of the world's leading roboticists, which we've brought together here into Heidelberg in Germany the last couple of days. The major focus of the last days of discussion and what we will be reporting on today has been the concept of life and robotics, and how robots are there. We use robots to also learn about life and to use the concepts that we learn through these study of robotics to improve and create robots to assist humans and the tasks in our everyday life. This event has been made possible through the generous support of our partners, KUKA and the Queensland University Technology, who have also been part of our discussions and involved in the last day's meetings. First of all, I'd like to introduce you to our panelists. So on my right, we have Ken Goldberg from the University of Berkeley in California, or University of California, Berkeley. Aude Billard from Lausanne. From the École Polytechnique, Fédérale de Lausanne. Also, Oussama Khatib, Director of the Robotics Lab at Stanford University. On my left is Bruno Siciliano, Professor of Robotics from University of Naples, Federico II in Naples. Yoshihiko Nakamura from the University of Tokyo. We also have Ruzena Bajcsy from University of California, Berkeley. And finally, Greg Hager from Johns Hopkins University. Thank you for joining our discussion. I hope you'll find it interesting. We'll be taking questions from here, the colleagues here in the room, but also anyone out there in our virtual global audience. If you have a question, please respond to the Twitter tag. And I'll now hand over to Oussama to briefly provide a little bit more detail on the concept of life and robotics.
Thank you, Chris. Through history, humans have been always interested in creating artifact machines in their image. And the development of robotics really came with this model of the human. However, the development of robotics itself brought a lot of foundations for understanding many aspects of motion, of behavior, of skills that were always inspired by the human. And little by little we found that robotics was not only good for robots. Robotics allow us to understand better articulated body systems, to understand human and animals and many creatures that are in life. That understanding and the body of science being developed in robotics brought us to think, well, maybe now it is the cycle that we are closing between life and robotics and life. And this was the prompt for this symposium that I should say brought one of the best representation of the expert in the field of robotics and life. In fact, we are so pleased that our colleagues joined us here in Heidelberg, took time for this intense 3 days discussion, and I'm sure we are going to have more discussion in the rest of the day today to conclude and hopefully bring this to the whole community. So let me just pass the microphone to Bruno to bring about other aspect of this organization. Bruno?
Yes. Thank you very much, Oussama. And as also Chris said in the intro, we wanted to make this symposium, which ran for the past 2 days, as lively and as fruitful as possible. And then we organized our scientists into 4 working groups. The first one, you will hear the reports, the summaries from these working groups. The first one was a working group on knowledge, which was aimed at building knowledge by understanding the skills and strategies that humans, animals, and plants employ. And besides Aude, Billard, who is going to report about this working group, I'd like to acknowledge the contribution by Alain Berthos from Collège de France, Raja Chatila from Université Pierre Marie Curie in Paris, and Peter Cork from Queensland University of Technology. The second working group was focusing on design, which is the natural way to apply this knowledge to design better machines and better robots. And besides Yoshihiko Nakamura from University of Tokyo, to my left, also the group took advantage of the contributions by Aline Albushaffer, who is the director of the Institute of Robotics and Mechatronics at DLR in Oberpfaffenhofen in Germany, Tamim Asfour from Karlsruhe Institute of Technology, who is almost local here in Heidelberg, and Antonio Bicchi from University of Pisa and Italian Institute of Technology in Genova. The third working group was on interaction, and the thread was to understand and to speculate on the human-robot interaction as well as on the human augmentation. And besides Ruzena and Greg, who are representing this the work of this group, I'd like to acknowledge the contribution by Nancy Amato from Texas A&M University, as well as Etienne Bourdet from Imperial College in London. Last but not least, and even more importantly, we focus on impact. And as Chris said in the introduction, the goal was to analyze not only the societal impacts, which are obvious when we come to using robots one day in our society, but also a number of ethical considerations. And besides the report by Ken Goldberg, the group also featured Roland Sigvart from ETH in Zurich, Jean-Paul Lemonde from La CNRS in Toulouse, France, Daniela Russe, who is the director of École at MIT, and last but not least, Guglielmo Tamburini from University of Naples, Federico II. We worked, apart from these working groups, we really worked together, and also I'd like to acknowledge the contributions by Richard Hodson and Owen Vaughan from Nature, as well as Jonathan Lowe from University of Kent, and Angela Jaiprakash from Queensland University of Technology. So I think now we will hear the summaries of these working groups, and then we will just continue the discussion.
Yes, so we're going to start talking about the report or what has happened in the knowledge team, and reporting on that is Aude Billard. Aude, so something which also Oussama mentioned in his introduction as well was a major theme is how we use robots that can be tools for engineers to better understand biological life. Could you expand a little bit on that concept?
Thank you. Certainly. So the first thing that we discussed at length was the fact that robots are machines that need autonomy, and to be autonomous, then you need knowledge, and you need to acquire this knowledge in the first place. And so in order to acquire this knowledge, we started toying about the idea of, can we acquire it completely? Is learning the tool the solution? How much do we need to already have laws of control, laws of autonomy? And what does that mean to have laws of autonomy? How much do we need to know about the kinematic of the robot, the dynamics of the world? How much do you know about the body of the machine and its environment? So knowledge, learning, how do they go hand by hand? This was a lot of our concern, and we tried to discuss how to have lifelong learning, having machines that continuously learn, relearn, adapt, and how can we store this knowledge. But the most important thing for us was that robotics is a science that provides information to science at large and to biologists potentially, and to humans. And so we need to be able to extract the knowledge that our robot learn when they interact with the world in a way that is interpretable for human beings. So this was a key concept, the interpretability of what is learned and what is programmed in the robot. And we struggled with problems as to how to make this interpretable. What does that mean to have a communication system with the robot? We also discussed a lot about the dichotomy between brain and body. We love the idea of saying that we have brains and bodies, plural, the fact that we have different type of robots. They don't look the same. We have some of them, they are tiny, they look like insects, others look like humans. They have different bodies. They may have similar brains. We go back to the learning and the knowledge. So do we have similar algorithms? Yes, we do. Do they get to be changed as the robot learns, as the robot interacts with the world, or as the robot gets to have some knowledge about its own body? And so these are more questions than answers, and we love the fact that we are creating problems with robots in a good sense. So we are asking questions, and we are turning to biologists to help us answer some of these questions.
Exciting problems, always.
Yeah. Oussama, I know you've talked about some examples in this direction before. Perhaps.
Yeah. Well, let me have your microphone. Actually, while you're talking about the diversity of robots, you could think about the diversity in biology and life, and that diversity is what also really interesting. I mean, in terms of behavior, interacting with the physical world, I mean, dealing with the resources and moving and using tools and doing all kind of things that we see both in life and in these artifacts, these amazing machines that we are building, that are bringing that also interaction between among themselves and with human. I think probably one of the most important aspect of understanding is how we can translate and encode that into things that can be used by those machines. And I think the team in design was the one who was thinking about those issues. So I would like to hear from the design team, and maybe I'll give you back the microphone.
Thanks. Yeah, Yoshi. So yeah, as you said, yeah, your focus was on design. Yeah, what were the main topics that came up?
Okay, so in the design team, we discuss about many aspects of design. But first of all, I have to point out that design is hierarchical system, and there are many levels of design. And we just listed up 4 major keywords to describe the current and future importance of design. The number 1 is the creative design. The design does not only mean to choose appropriate components and make a system. It includes creative activity to listen to spoken and unspoken voices of society and people, and abstract and put them into the specification and the development of a system. This is very important creative part of design. The number 2, the human life and biology. The robot in and for human life needs human models implemented into various levels, from anatomy, behavior to cognitions. The knowledge of biological system provides direct and indirect living examples of principles, functions, and structures for the design. The number 3, this is a new keyword, but holo design, or model-based co-design. The global scope of the key of robotic system design. This is a global scope. The physics, including geometry, kinematics, and dynamics. Mathematics, including planning and control. Use of models of human behaviors and data structures. They must be considered and optimized concurrently. This concurrency is a very important part. The interoperability of components of hardware and software is a requirement to make this holo design possible. Number 4, reinforcement of interdisciplinarity and societal concurring. The creative paradigm of robot design finds significant challenge in contributing tools for scientific research and building hypotheses for biological systems, including human activities in the society. The societal attachment and the collaboration with the industries are to be reinforced in the robotics research. The interdisciplinary research should even more promoted in academia. The publication environment does not exist for this interdisciplinary field. The publishers and the experts of reviewers in interdisciplinary research should grow in this field.
Thank you, Yoshi. I think I wanted to touch back on one of those points that you made because it's related to the previous topic as well. And that is the topic where through robot design, you're coming up with models which are then can be hypotheses that can be tested by biologists and other sciences. And that was coming back to the previous point in that we were building knowledge through actually designing robots for a wide range of not only physiological but also societal, behavioral, and psychological studies as well.
Well, I mean, the two of them are completely connected. So think of designing a robot that doesn't have any sense of touch, and this is what we've been doing for years. You're very limited in what you can do. You can only position yourself. It's like having a robot that is completely blind. Then it's going to be also very limited in terms of the navigation capability, the prediction capability. So you need to design the sensors and the body and the actuation, but assume that you design a robot that has all these tools, all the tactile sensing, all the vision, and then you provide it with a very simple algorithm that all it can do is just moving forward, left and right. And it's not capable of using the sensor or adapting to the noise or modeling the noise of each of the sensor or having a different clock. And it's just, you know, it's an algorithm that runs at 10 hertz and every of these sensors runs at 1000 hertz. It's just wrong. So you need to design both in combination.
And that once you have all those sensors and everything, I think one other point which you were talking about is also the learning part and the robot in context in the environment, and how that is important for robots to evolve basically.
So one of the challenges in the physical interaction, as just Aude was mentioning, is the fact that we need to interact with the world, changing, assembling, putting, making contact, and doing that at multiple points and in very challenging ways that humans do. So we look at human and we see human skills. Human skills are amazing, but how can we get the robot to do those skills? It means that we need to understand human. So now suddenly we want to understand human. We go and start to model and put more information in describing how human is performing those tasks, how muscles are moving and producing forces, how compliances are produced, and all these different things. And suddenly what we realize is that these things are very useful actually for human, more than maybe what we are trying to do for understanding a skill. So this is the process that we've been going through, that was to develop musculoskeletal models to really track motions and try to isolate vision from tactile and try to understand how humans perform different tasks. And by repeating these different things, we get insights into human behavior that are very, very deep and interesting for human, not only for our task of getting those skills from the human. So at the same time, some of the control methodologies human use or life use was amazing for us in terms of how we can capture that and map it to the robot, the machine, simplify many of the challenges that we used to have when we were rigidly exploring every aspect of the motion of the machine. Human move fluidly in ways that makes the natural motion really surprisingly amazing to the eyes, but if we look what is behind it and what kind of abstractions the human is using for those motions, we can reproduce that in ways that are much simpler actually for the machine. So this interaction is what is really remarkable, the interaction between what we observe in life, what we can map to the physical world through these artifact robots we are building, but there is a science that is created through robotics, building those algorithms, understanding, and bringing back to contributions to human betterment. And I think that is what is really exciting.
Yeah, so I mean, a few times there you mentioned the term interaction. So robots interacting with their environment, so that they can perform, perform other tasks within the environment, but also talking about how humans interact with the environment, and more importantly is how humans and robots can interact together. And that was the topic of the third team, where Ruzena and Greg were involved. So I'd like to ask Greg, so what are some of the key topics that came up in the interaction group?
Well, so we echoed, in fact, many of the themes that we're already hearing from some of the other panels. We're really in our mind, at the beginning of the age of interaction. It's really, I think, a very new concept that we start to think about designing robots to be fundamentally interactive systems with people. And so when we started to think about the scope of interaction, we've talked a lot about the physical world and about how one would interact with the physical world and how a robot would interact with the physical world. But there's also, as you suggested, there's the social realm of interaction and ultimately the cognitive realm of interaction. So it's not just exchanging energy and force between people and robots, but ultimately it's moving in a friction-free way among people and then finally exchanging information with people that's essential for a robot to perform its task. And so as we thought about those areas, and we thought about the fact that increasingly we're going to design for people in mind, we had a few principles that we thought were really important for the community to start to articulate and to work through. So the first is what does it mean for a robot system to be safe? So at the physical level, what does it fundamentally mean to work with a robot that's safe? And the field's made some progress in that direction. We now have human-safe robots operating in factories. But then, as you move up the hierarchy, what does it mean to be trustworthy? What does it mean to understand a robot system and to trust its capabilities and understand its capabilities? A part of that is transparency. How do you understand why a robot is taking the actions it's taking, and are those actions understandable in the context of how a human, for example, would understand and perform a task? And finally, what does it mean for a robot to be socially acceptable? We had a longer discussion about the question of to what extent should robots emulate people and act like people, and we should be trying to design toward that type of social interaction, and to what extent are robots a fundamentally different entity. And really, when we think about design principles, we should be thinking about designing towards principles that are reasonably unified and common across robots that again give people comfort that robots interact in a certain way in society. One of the other observations about this is that right now much of the work in these different areas, you think of the physical, the social, the cognitive, it's really happening very much in isolation. There are people who focus on social robotics, there are people who focus on the physical level of interaction, more on the AI level and communication. But there's not really yet threads connecting them. And I think one of the grand challenges as we move forward is to understand how do we connect the physical, the social, and the cognitive in meaningful and generalizable ways across applications. Another theme that again I think echoes the other panel is the notion that as we advance the science of interaction in robotics, we're going to advance the science more broadly. So think, for example, of psychological science or social science, where you're developing theories of interaction or you're developing theories about how groups interact. right now that's a science, and you study and observe and you build models. But robotics is an opportunity to deploy those models and to test those models. It's a way to build artifacts, and it's a way to build new tools and new forms of understanding that in fact will also advance the science for our colleagues. And so as we move this field forward, I think the opportunity for kind of enlarging the tent and bringing in social science and even humanities into the science of interaction is going to be a huge opportunity for robotics, and also an opportunity for, again, the broader scientific community. So those are at least some of the main themes that we touched on in our panel.
Ruzena, would you like to add to that?
Well, I just want to add, to me, robotics is all about the robotic science. And its hallmark is the integrative and the methodology that we develop, which is we make a hypothesis, then we design experiments or just simply make measurements, build models, then we build test beds, and then we validate our models. This whole chain of methodological steps is extremely able to predict scientific results on multiple scales, starting with molecular, then organ level, body level, and even at the societal level. So in that sense, to me, robotic science can reach and be part of a much bigger activity of scientific endeavor.
Well said. I wanted just to make a historical note about the fact that the interactivity between robots and human started at the beginning of robotics, when the first robots were simple enough to be teleoperated. So human, I mean, these were the first robot, and the human would interact with those robots, controlling all the joints, and they're doing one-to-one motion. Robots became more capable, more complicated to be controlled, and more autonomous. We went all the way in industrial robotics to completely isolate the robot, but by structuring the environment and program in details their motion to do the production, and we have now millions of robots working around the world. But I think what is really new about this era of robotics is the fact that robots are not anymore in the cages, and robots are out interacting with the human. And the science of that interaction is so critical. So critical, and these robots are going to be very different from the industrial robot. They have to be safe, as we said, but also they have to perceive intent, and they have to understand so many other things than just running through a program or pre-programmed behavior. So this is really interesting. We're going back.
Emphasize the scientific methodology that we have to go through is applicable in many different areas of science. And the critical point about robotics is that we not just model, but we also physically have to interact with other robots, with people, with other environment, and that physical interaction reveals new phenomena.
Absolutely, absolutely.
So actually this topic which you just brought up, co-robots, collaborative robots, is also something which is a major theme from the impact group. Maybe that's a good place to start, Ken, and telling us a little bit about what was discussed in impact.
Thank you, Chris. Well, robots have had a long history in our imagination that precedes the science and the research. And they really operate very interestingly as a metaphor about what they can reveal about human nature. So the group stepped back a little bit and thought about how they're positioned in terms of society and social impact. And one thing that we really, we spent a lot of time on was the very, very popular headlines these days about the future of work. And even some very distinguished publications are reporting that robots are on the verge of stealing many jobs. And there was a almost universal consensus here at the meeting that we're quite skeptical about these predictions. That despite the recent advances in computer vision and speech recognition and game playing, I mean, certainly it was a breakthrough that we were able to. The AI is now able to defeat the world champion in Go, and these are beautiful results. And the entire area of deep learning is very exciting, and also there's been a huge investments, unprecedented investments in the industry, including all the tech industries in AI and robotics these days. But this does not necessarily imply that we will soon have human equivalent robots, and we feel it's important to convey that because as Ruzena just mentioned, the physical interaction with the world is quite unforgiving, and that the ability to manipulate and control contacts and the forces of nature are extremely difficult and have resisted our ability to formulate and to have reliable robots. So, and a key issue is the fundamental uncertainty in the world, that despite all the advances in sensing, that we still have to cope with the fact that we don't know the precise positions and orientations of everything in the environment, and that those minor errors can actually lead to quite catastrophic results. So we want to push back a little bit on this expectation. So for example, the idea that truck drivers are going to lose their jobs, that all truck drivers will be eliminated shortly. We're very skeptical about this. The sense is that probably on the freeways it will be true, but not necessarily on city streets, and that at the same time, we also want to be respectful of the issues, of the concerns, that if there are advances that we don't anticipate, we should be keeping a close eye on those evolving, on those technologies. And so we should look for signs, and this is where the communication is very important. And the research has accelerated dramatically in this field to the point where new results are being shared almost daily, and in a number of different venues. And so that's very important, because for all of us to stay aware of breakthroughs and developments, because it is important that we share this and alert each other and our colleagues if there are advances that we think will trigger this kind of widespread disruptions that are being predicted. So that was the very big concern from the society perspective. We also see a huge potential, as has been mentioned earlier by Greg and others, about the co-robotics, this idea of robots working together with humans. And that this is the idea, instead of thinking about a singularity, we might posit a multiplicity where people and AI collaborate in new ways. And in fact, AI may help us understand the importance of collaboration in new ways. We think it can reduce tedium in many applications, including driving. It can increase safety for human drivers. We certainly think that is going to be the case. And also, it will improve performance, for example, of surgeons who may be able to use robots in an assist mode to perform surgery with more accuracy. So we see a lot of potential there, again, for robots to enhance human work. And then the other two are that we are acknowledging the aging population in almost all countries, and the need for robots to be able to assist in homes. So one that we discussed that we believe is within reach in the next 10 years is the idea of a robot that will not only just will clean the floors, but will actually declutter, pick things up and put them away, which could have a great value for senior citizens. And we believe that this is possible, and will probably, the prediction was that it will be an auto company, because auto companies are very good at managing designing complex systems, producing them at reasonable costs, and also provide the service centers to be able to service such devices. So we think that could be done within a price range that would be accessible to most senior citizens. And then the last thing we thought about was the idea of robots, the potential for robots to inspire the next generation of engineers. that they are that we think more needs to be done and to think about how to design robots that could be used for teaching, and particularly that would attract a diversity of engineers of different genders, of different backgrounds, because we see that that is going to be so important for the robots of the future, that we have a diversity of researchers who are contributing to their design.
Thanks, Ken. I'd like to touch back on one of your topics and what was discussed here previously when it comes to actually having more robots in our lives was the concept of trust and what we expect robots to do for us. And especially when something has a degree of autonomy, suddenly we expect it to be able to do so much more than our washing machine does. This concept of trust and what expectations, I think, was very interesting in the interaction group.
Yeah, well, yeah. So as you suggest, as we see increased complexity in systems, one of the things we find, and in fact this emerges in user studies too, is with a complex system comes an increasing difficulty for users to build a mental model of what the system might or might not do. Part of what allows us to trust each other or to trust your car when you're driving it or your washing machine or whatever is, you trust that when you press on the brake, your car is going to stop. And you have that model in your head, and you can kind of use that as a basis for your driving behavior. You trust other drivers are going to generally adhere to the laws, traffic laws, and so you can use that to govern your behavior. So as robots become complex and as they increasingly interact with us, trust is going to emerge in some sense from our ability to predict what they do. And I think one of the interesting aspects of that is as they enter more and more safety critical applications, we're talking about autonomous driving now, you're talking about, Ken speaking about elder care, now you're talking about robots interacting in an intimate way with people. And so the level of trust really has to be very, very high for us to be able, for the public to be able to accept those systems. And conversely, I think the contrapositive of that is safety. These systems have to be very safe so that we don't run the risk of losing public trust in systems due to inadvertent actions that may have been unanticipated by designers. So I think the notion of how do you build trustworthy systems that are transparent, predictable, and safe is a fundamental issue in robotics.
Well, I just want to add to that, because one of the things that is that's the big new wave of excitement right now is around deep learning, and it runs counter to the traditional approaches of robotics, which are based on analytic models. And for analytic models, we can have very nice predictions. We can often prove guarantees on their performance and bounds on their behavior. But this may not be the case with deep networks, and that I think it comes right to this trust question. We want to be able to trust these systems, and we need them to be able to be analyzable, and I think that's a huge forefront for research.
Well, related issue, just you mentioned deep learning and kind of more complex systems that are black box, they're not transparent. A part of that is also, can we start to design systems that have an understanding of their own capabilities and are able to communicate what they are and are not capable of doing and why? Because again, that leads towards the trust issue. It's one thing to do something wrong, it's another to say I'm incapable of operating in this environment and here's why this is the limitation of my behavior.
Yeah, I'd like to elaborate the concept, and I think it's like what the research community is currently tackling is also to find quantitative and objective metrics for safety, dependability, trust. It's like, and to this extent, I think our mission should also be that of promoting systematic benchmarking in robotics, which I think, this has been proposed at various levels in research projects, but I would foresee a sort of a strategic effort by the community, because if we want to develop such systems on an industrial and commercial scale someday, sooner or later we have to tackle this, and I think it's our role really to find just usable tools to assess the performance of cooperative robots with humans.
Indeed, one of the really interesting thing from this discussion is that we see that, well, we need safety and we need to guarantee safety, which means we cannot really make use of the same design concept that we were using in industrial robots. And today, there are so many robots today around the world are rigid because they need to be precise, they need to be accurate and fast, efficient. Now we have new concepts that are being little by little brought together into the this idea about human-robot interaction. So we talk about soft actuation, we talk about soft robotics in general, and we are bringing new way of putting different actuation systems, skin, and all kind of new designs that would be suitable for that human-robot interaction. We have to guarantee it, which means that it's not enough to be safety through software or safety through some sensors that could fail eventually, but we really need to have full guarantee that that interaction will not cause harm to human. And I think these are really interesting challenges that are bringing a lot of novel research in sensors, in material, in ways of integrating mechatronics and molding all of these together in the hardware of the robot system. So.
I just wanted to say I really reject approaches that say, look, Ma, it works. Not good enough for me. We are engineers, and we are obliged to find the boundaries and say, within these boundaries, I guarantee it will work. And I guarantee you because, and I know that because, this business that it works and we don't know why it works, I don't buy it. And
actually, an important part of that, Ruzena, is also that it's our duty to also share where it doesn't work and demonstrate the failure modes very clearly.
Of course, if you know the complementarity, you know my famous question in PhD exam is, okay, you told me what works, now tell me what it doesn't work.
We have a whole conference devoted to validation, and we appreciate always papers who bring, well, the theory doesn't work really in here. And I think this is very important.
So yeah, we have another 8 minutes of our panel discussion. I also wanted to come back to one thing which was mentioned in the interaction part, and that was how, you know, robotics as a discipline or as a science should become more inclusive as a big tent for many diverse areas of humanities, science, and engineering. This was also a topic which was brought up in the knowledge section, where the concept was that we really need to have people with other skills interacting in the area of robotics. Or did you want to pick that up?
Sure. So we really brainstormed the fact that we have to learn a lot from how humans develop and develop these skills that we so much want to have in robots. And I think this has been mentioned before, that we want to have robots to be very flexible, adaptive, learn. And, you know, these are keywords, but we certainly don't know how humans really do these things. And so there are other disciplines such as developmental psychology, biology, even, you know, ethics and philosophy that study this at length. So bearing in mind that we want our engineer to understand what they program, we still believe that they need to have a very strong background in math, physics, and all of those. But we like also to have them, you know, get exposed to this other discipline, whether it's during their PhD with having really programs that are jointly organized between biology, psychology, and engineering fields, or having longer stay during the postdoc and afterwards. So we believe that this is absolutely necessary for the field. But once more, stammering in that we want our engineer to understand the math and the algorithms behind before they go and move and use other tools.
There's also the converse of that, though, which is, in the future, you would like to believe that perhaps, psychologists, sociologists, ethicists might actually embed themselves in the robotics community and bring their ideas into the community and seek to understand robotics. One of the things we talked about is, in the future, will you actually start to think about things like, engineering ethics or ethics engineering? Or psychological engineering, or social engineering, where it really is a hybrid of the field. It's not just kind of our students learning about it, or maybe them coming and giving us some ideas, but it's really a deep embedding and a cross-fertilization. And I think that's really an opportunity for robotics at this point.
Yeah, this was...
Can I make a comment from design point of view? So the biological system or societal system is hierarchical and very complex system in multi-scales. I think the robotics has a very strong tools for modeling the complex system and connecting the systems of different scales. And if we are missing some knowledge, of course we want to have all the knowledge, but if we have something missing, we can make the feasible or reasonable model for the missing area, and we can make the whole system as in the simulations. So I think this is the very strong part of the robotics contribution to society or science.
I just wish to add this, this issue of cross-fertilization has been very, very strongly felt in the group that gave rise to this long time project of the Springer Handbook of Robotics, because just in which most of us were involved, and the main point was that in the last 50-60 years, I think we have well assessed all the core methodologies and technologies which are enabling the design and realization of advanced robotic systems. I think our attitude as robotic scientists is already that of a wide outreach towards other community. I think we share the common view that further progress in the field will not happen within this group, but as you were saying, will happen at the crossroads with other disciplines, and this is what's happening in robotics, and probably the gradient could be much faster than we might think about.
And I think one other point that we should really stress or look into to finish off this panel is that robots are there to assist, or our motivation for creating them is to help us do things. Oussama, would you like to expand on that point? They're not there to take over our lives.
Yeah, there is a great concern about robotics today in terms of and AI and how robots might really take over our lives, and sometimes we feel in the robotics community that we are flattered by those high expectation of the potential of robots that we are working on. Knowing robotics and knowing the field and the challenges, and knowing how difficult it is to really bring, first of all, the capability to interact with the physical world, and then connect that with cognitive capabilities to reason, and then to get the experience translated in intuition about different actions. The problem is huge. So today's robots are coming out of their cages to interact with the human, and more we are going to see something very simple. Something like we can describe in two words: muscles and brain, and the connection between the two. Muscles are going to be supported by the robots and the brain supported by the human, and the two are creating a new synergy. There is a lot of brain in the robots and there are a lot of muscles in the human, but essentially removing the pain of a task and reaching places that human cannot reach, and working with the human intuition, experience, and expertise. And we don't want to be operated by an archaeologist, we want a surgeon to operate, so the expertise in human is amazing, and extending the hand of the human to reach in those areas is quite important. So this connection with the human is going to be really remarkable in the way we will be using robots in the coming years.
Thank you very much. So I hope we've been able to give you a bit of an insight into what we've been discussing in the last couple of days, some of the key opportunities and challenges which the robotics community, or the wider community involved in the project, which is robotics. Yeah, we hope you've enjoyed it, and we've certainly enjoyed telling you about it. Thank you very much.